Hello and welcome you all in the last class of the IAR filter. The topic is called the bilinear transformation technique. This transformation technique is also known as the Tuskin's method. Tuskin's method. The main use of this kind of Tuskin method or the bilinear transformation technique is in the use is digital signal processing, and discrete time control theory to transform continuous time system representation to discrete time and vice versa. To convert, the third point is to convert transfer function that is HAS of a linear time invariant filter, that is LTI system, the linear time invariant filter in the continuous time domain to a transfer function that is HZ or HDZ of a linear shift invariant filter and in the discrete time domain. So in this the process is going to the method and the prerequisite of the topic I already discussed the last class, that is the wrapping and pre-wrapping effect. That is the prerequisite of the transformation technique based on the problem. Let's discuss the steps for solving the bilinear transform technique. So the steps for solving the bilinear transform technique. First point is find the pre-wrapping analog frequency using the formula. Some formula is there. So first point is find the pre-wrapping analog frequency using a formula that is omega equals to 2 by t tan omega by 2. I think you are all familiar with this with this formula, because you have already, I think you have already done the wrapping and pre-wrapping topic. Okay, step number 2, that is using the analog frequency find Hs, that is a transfer function of the analog filter. This is the second step. So Hs, that is already discussed, to convert the transfer function Hs of a LTI system in the Hz. So our motto is to find the Hs, then convert that Hs in the Hz. Okay. Step number 3, select the sampling rate of the digital filter that is the t in second per sample. Last is a substitute S as 2 by t into 1 minus z inverse by 1 plus z inverse into the transfer function that was found in step B, that is in the step. So first step is we have to find the analog frequency using the formula. That means we have to find for the Hs is finding the first target is find the Hs value, and for the Hs we have a value of the sample, that is sampling rate, that is a t. It is mentioned in the question. Then substitute is as this value 2 by t. T is given into t will given in example 1 minus this value. So we have to substitute this value s in the top in the this line. That is step number 2. Then we will find the answer in the Hz. So let's do a problem. So how to solve the problem we can discuss. So let's take a simple example, and the question is apply bilinear transformation to Hs. The Hs value is given with t, that is the sampling rate is 1 second. Find Hz. That means we already have this value Hs. So already we have the step number B. Hs value is there, is given, and t is also given, that is 1 second. So step number B Hs is already given. Value of t, step number 3 already given. We have to just put the value s as this value in Hs to find the value of the Hz. So simple problem. Our first step was find the pre-wrapping analog frequency using the formula, but we don't need to find the formula because we already have the step number 2, that is Hs. So we already have the Hs, and to find the value of the Hz we need to find two value. One is t and the second one is s, where t is already given 1 second, and we have to put the value of s in the equation. Simple problem. So Hs is given. Hs is 2 by s plus 1 into s plus 2. So it is our step number 2. Next is substituting the value of s. That means substituting s value is 2 by t from the formula 1 minus z inverse by 1 plus z inverse, where we know the value of the t is given, that is 1. So substitute this value in Hs, that means the given question Hs, to find the value of Hz. That means hz equals to 2 by s plus 1 into s plus 2, and put the value of s as this value, where t value is 1, so that means 2 into 1 minus z inverse by 1 plus z inverse. So after putting the value of s, the final answer is like 0.166 into 1 plus z inverse whole square by 1 minus 0.33 z inverse. So this is the final answer. So the problem is very simple. So let's take a problem where hs value is not given. So we have to start from the step number A. So let's have the problem of this type. So the example number 2. So using, that is example number 2, using bilinear transformation, design a high pass filter that is monotonic in pass band, which frequency, there is a cutoff frequency, cutoff frequency is 1000 Hertz and in 3 decibel. Down at 10 dB at 350 Hertz. The sampling frequency is 5000 Hertz. So this is a problem. So you have to keep in mind that 3 dB is our alpha p, 10 dB is the alpha s. You have to put the values. So the first step is to find for the pre-damping annual frequency. So in the question the given part is alpha p, the value is 3 dB, and for high pass filter omega c is equal to omega p, the value is omega means we know that 2 pi f, so 2 pi and frequency value is 1000, it becomes 2000 pi radian per second. Okay. Next is alpha s, the value is given 10 dB, and omega is omega s, simple 2 pi f, that is 2 pi, frequency is 350 frequency is 2000, 700 pi radian per second. And we all know that the t is 1 by f, time period is 1 by frequency, so 1 by 5000, t becomes 2 into 10 to the power 4 minus 4 second. Okay. Next, so the formula that was given in the step number 1, 2 by t tan omega p t by 2. For p, that's what is given p. So value 2 by t, the t value is 2 into 10 to the power minus 4 into tan omega p value is 2000 pi. Again t is 2 into 10 to the power minus 4 by 2. So this value becomes 10 to the power 4 tan 0.2 pi, and finally it becomes 7265 radian per second. Again you have to find for the omega s. Simple formula is same, 2 by t tan. Now it is not p, should be s, t by 2. 2 by t value is fixed, omega s value is 700 pi, t is fixed by 2. This value becomes 10 to the power 4 tan 0.07 pi. That means 2235 radian per second. So we can draw the characteristics also, the graphs. We can use the space also. So we know the values. Omega p is this value 72765, and omega s is 2235. So the characteristics are monotonic in both pass band and stop band. So therefore the filter is a Butterworth filter. So we know how to solve the problem based on Butterworth filter. So I can write the characteristics. Are monotonic in both pass band and stop band. So from the previous example of Butterworth filter, we can conclude that the filter is Butterworth filter. So we know the characteristics of Butterworth filter, how to solve the problem based on the Butterworth filter. So in case of Butterworth filter, you have to find the order of the system. So first step was the find the order of the filter. So step 1 should be the find the order of filter. The formula was n is so this is root over 10 to the power 0.1 into alpha s minus 1, and it is 10 to the power 0.1 alpha p minus 1. So formula, put the value in here, 10 to the power 0.1 into 10 minus 1 by 10 to the power 0.1 into 3 minus 1. by alpha omega s by omega p. The value is 7265 and this is 2235. So the value becomes 0.932. So this was the first step of Butterworth filter. The second step is round off in the next higher order integer. That means n becomes 1. So for the value of n is equal to 1, so you have to find the value of the hs. So from the previous table in the class of Butterworth filter, we already discussed. So if the value of n is 1, 2, 3, 4 like this, so what should be the value of the numerator and denominator? The numerator value is 1 fixed, and for the denominator it is changing. There is a table also there. You can just check the previous class. So if the value of n is 1, so for n is 1, hs becomes 1 by s plus 1. Okay. And the next step was find the value of the omega. Find the value of the omega c. So omega c already known. The value is 7265 radian per second. And you have to put the value of the omega c by s in place of the s. So s should be omega c by s. That means omega c means 7265 by s. So you have to substitute the value of the s by this value. That means hs was 1 by s plus 1, where s value is 7265 by s. So hs become s by s plus 7265. This entire thing of the Butterworth filter, that is from the last step, that is from the n, finding the value of the order, this is already discussed in the previous class of Butterworth filter. Just go through the topic. So after finding the hs, we already discussed the last example where hs value is given. So here we can find the value of the hs, then we have to find the value of the hz. That means now we have to use the bilinear transformation. So hz becomes hs, where we have to put the value of s as already discussed, 2 by t by 1 minus z inverse by 1 plus z inverse. That means s by, so hs becomes this value, s plus 7265, where s is equal to 2 by t was the fixed value, that is 1 by f, into 1 minus z inverse 1 plus z inverse. Just solve the value. We can find the value like this: 0.5792 into 1 minus z inverse by 1 minus 0.1584 z inverse. So this is the value for hz using bilinear transformation. Thank you. So this is the topic of this last topic of the IR filter. From the next class we will discuss on the FIR filter. Thank you.